A FRQ type problem involving citric acid and buffers. Citric acid is very, very common acid. Let me just pull up a page describing it. When it's crystallized beautifully here, it looks almost like little lumps of ice, but it's a solid at room temperature, and it's really, really commonly found. It's found in lots of plants, lemons, oranges, grapefruit. And in fact, if you get some lemons, you can get 3/10 molar citric acid. Oranges are about 5,000 molar. It used to be that they produced most of the citric acid using fruit. That was a common arrangement, but during World War I, you couldn't get a lot of it from Italy because of wartime conditions. Now it's produced by using a mold. You feed this mold sugar, and it produces tons of citric acid. They precipitate it out. 50% of the citric acid that's used in food processes and beverages, and it's even used in detergents, is made in China. Citric acid, and you have some orange juice, you have some lemon juice, you've got some citric acid. Let's go to the problem right now. It's a triprotic acid. It can lose one proton, it can lose a second proton, and then a third proton. And each one of these acids successively will end up having its own Ka. And we can use these Kas to find the pKa. It's going to be pretty easy. We just get our calculator and we know negative log, negative log, negative log. I've done them already. The answers make sense. Here's our first Ka, our strongest of this triprotic, of course. It's close to 10 to the negative 3. 7 times 10 to the negative 4 is close to 10 to the negative 3. And notice we have an answer, 3.12, and we can keep doing this all the way down. In fact, you'd figure, okay, a 3, about a 5, maybe about a 6, and indeed, here's our various pHs, pretty much what we expected. A 3, there's roughly a 5, and this is between 5 and a 6. So notice the pKa's go up as our Ka's, our ionization constant, goes down. That's what we expect. Nice, easy numbers to deal with. And you do this anyway because this is a buffer problem. And we're going to need to know these pKa's if we're going to deal with answering this. So here they are. We're ready. You saw how easy they get by now. You've done a lot of negative logs. Well, here we go. Common use for buffers is to calibrate pH meters. pH meters are a little fussy, and you can adjust them and calibrate them. And the calibration for most pH meters is 4, and we're going to use the citric acid solutions, which are inexpensive and easy to weigh out, to make the buffer. Well, when you make a buffer, you want to use the pKa because the pKa is the pH when you have an equal amount of acid and base. So here's our citric acid, and its conjugate base is the sodium citrate. It loses a proton, it gets a conjugate base. There we go, Bronsted Lori. So when you have equal amounts of citric acid and sodium citrate, you would end up having a pH of 3, equal amounts. Now, if you had a mixture of sodium citrate and disodium citrate, where this is the acid and this is our conjugate base, and we had equal amount of those, we'd have a pH of 4.77. Well, that's too high. We want a pH down to 4. We're going to use the combination of the citric acid and the sodium citrate. You'll want to always find the pKa that is just slightly lower than the pH you want. It can't be higher. So slightly lower is better because this is the two mixtures we're going to put together to get a pH of 4. So let's look at our little mixture here. Here's our little pH diagram. And we know if we have an equal amount of our first acid, our citric acid, and our conjugate base, we get a pH of 3.13 right here. That's what this arrow is. But we want to have a pH of 4, which is going to be, let me pull up an arrow. We want a pH here. Now with equal acid and equal base, we have a lower pH. If we increase the amount of base, we'll make our pH higher, and that's what we want. So we're going to need a little bit more base and a little bit less acid, and that'll get us our buffer. In making a buffer, how will the concentration of the acid compared to the concentration of the base? Well, 3.13 is where we're at right now. If we have equal acid and base, but we want a pH of 4, so we're going to have to get more base. 3.13, this is what you got to memorize. pKa is the equal amount of acid and base. If you want a higher pH, then you better dump in some more base. So our ratio is going to be a little bit less citric acid and a bit more sodium citrate to get that pH to this 4 level. Now, here's the two equations that you really should remember. I mean, you can look them up and derive them, but when you get your flashcards to memorize for the AP test, you want to know that the concentration of the acid, what you're going to be getting with the pH, is the Ka times the acid-base ratio. So you get any three of these, you can find the other. And here's our Henderson-Hasselbalch, where we use it using pHs. It's the same thing mathematically, where you have a pH equals pKa plus log. In this case, the base is on the top. If we had a negative here, we'd flip it around, but this is the way they have it on the AP equation sheet. So you just have to remember that without the logs, the acid is on top. With the logs, the base is on top. When this asks what's the ratio of acid to base that you need, typically they like to have the acid on top, and that's what this question asks. So we would end up picking the ratio that we have here, where we have the hydrogen ion concentration is equal to the Ka, and here's our acid-base ratio, where we have a little bit less acid than base. This is going to be a number that's less than 1. So I'll get my calculator out. Where is it? Right here. And I can put my pH that I want. I want to have a pH of 4 times 10 to the negative 4. I'm going to have to divide by this, divided by our 7.42 times 10 to the negative 4. Nice. If you know this equation, it's easy. Here's our ratio. I said it should be less than 1. Here it is. Definitely less than 1, because we have to have enough base to push the pH from the 3.3 that it would naturally be when it's equal all the way up to 4. Well, the answer is a little bit blurry, but I'll let you actually do the calculation. Now, I'm going to do the same problem, except I'm going to use the logarithms, just as sort of practice, because you could use either one of these. We could have used the log equation, or we could have used the pH equation. So let's look at this in terms of our logs. Here we go. We're going to put everything in, and in this case, we're going to have our pH that we want, 4. Subtract that 3.13. Remember to use the subtraction button, not the negative, to figure out the 0.87. That's the log of the base to the acid ratio. So we would want to get the anti-log of that last value. And there, I'd put in my second function answer, or I'd put the 0.87 in, and we'd get the ratio of base to acid. And we wanted the acid to base ratio, so we'll just take the inverse of that to come up with the actual answer. Again, that's a bit blurry, so I think you're going to have to do this one on your own to find out what the exact answer is. Last part of the buffer problem, the penultimate of buffer problems, where you actually have to give the amounts that are involved with things. Let's see, how many moles of conjugate base would be needed to be mixed with 0.15 moles of acid to make the buffer mixture with a pH of 4. Again, two ways of doing it. We can use this or this, either one, whichever you feel more comfortable with or easier to remember. And this one is be the same problem that we had up here, except we have the 0.15 moles of base as our numerator. And then you can also choose, if we prefer, the pH method, where we use the Henderson-Hasselbalch. I think I'd prefer to use this one because it gives me the answer pretty quickly, but both of these just involve a little bit of math and calculations on your part. Make sure that you just know what the acid is, the citric acid, and the conjugate base, the sodium citrate, and you're set. Now, notice we can use moles here, even though this says concentration, but because both the numerator and denominator are moles per liter, which is concentration, you can cancel out the liters because it's always per 1 liter for concentration. So you can use either moles or you use concentration when you solve these problems. There you go. Buffers. Henderson-Hasselbalch, KAs, pHs. Wow, that's something.